Get ready to torque your nuts, harden your springs, and forge your mind into a bulletproof study guide. We are mechanical engineering made simple. Welcome to the deep dive.
Today, we're really digging into something big, the essence of mechanical engineering. We're going to try and map out that journey, from just an idea, thinking about the whole system.
All the way to a real physical product, something tangible, efficient, and powered up.
Exactly. It's a massive field, obviously.
Oh, huge. But we've tried to structure this based on the source materials, breaking it down into maybe 3 core areas for you. First up is the strategy part, systems and strategy. How you even define the problem.
Okay.
Then we get into the making of the thing, design and manufacturing. And finally, how we power it all, think fluids, power, and efficiency.
All right, let's jump into that first pillar then.
Yes.
Strategy, systems engineering. The sources really hammer home this idea of issue formulation.
Yeah, and it's fundamental how you frame or formulate the problem at the very beginning. Well, that pretty much decides how you're going to solve it. It sets the whole direction. So getting that definition right is key.
Absolutely key. It involves figuring out the client's objectives, what they really want, what they value, that's value system design, and then brainstorming all the possible ways to get there, the alternatives.
Well, yeah. There's a catch, right? A human catch.
There always is, isn't there?
Yeah.
Yeah. Relying purely on human judgment, even from experts, well, it opens the door to cognitive biases. We all have them.
Right. We like to think engineers are purely logical, but these biases creep in, like selective perception.
That's a big one.
Yeah.
It's basically looking for evidence that confirms what you already believe or want to be true. You filter out anything that contradicts your preferred conclusion. It's like wanting a self-fulfilling prophecy.
And expectations is similar.
Kinda. With expectations, you give more weight, more validity to information that just confirms what you already thought. It feels right because it matches your existing beliefs.
It's easy to see how that happens when you're drowning in data. You grab onto what looks familiar, and then there's ease of recall.
Right. That's where you overestimate the likelihood of something, just because examples spring to mind easily. Think dramatic failures versus quiet successes. The dramatic stuff sticks, so you might think it's more common than it really is.
So, if we know about these biases, why are they still such a problem?
Because, well, knowing isn't always enough, is it? Biases aren't just about not knowing something. They're like mental shortcuts our brains take. So acknowledging this human factor, this potential for error right at the start, it means we need really solid objective processes later on.
Which brings us neatly to how we enforce that rigor in the physical design stage, DFM&A. Design for manufacturing and assembly.
Exactly. That's the framework. And it's useful to kind of separate the two parts in your mind.
Okay.
DFA, design for assembly, is all about the labor part. How can we make putting this thing together faster, simpler, with fewer steps?
Makes sense. And DFM?
DFM, design for manufacturing, focuses more on the components themselves, reducing material waste, making parts easier to fabricate, thinking about tooling costs, things like that.
And using them together. The results can be pretty dramatic.
Oh, absolutely staggering sometimes. The sources give this fantastic example, a motor drive redesign. They applied DFM&A principles.
Then what happened?
They slashed the number of parts, went from 19 components down to just 7. Think about that.
Wow, 19 down to 7. That's huge simplification.
And that simplification ripples through everything. Assembly time. It dropped from over 213 seconds down to about 86 seconds.
Less than half the time.
And the bottom line, the unit manufacturing cost, the UMC, it went from $47.22 down to $30.21.
That's a massive cost reduction per unit, almost $17. That's not just savings, that's a competitive weapon.
Precisely. That's the power of thinking about manufacturing and assembly right from the design stage. It's strategic.
So when you have potentially thousands of parts, how do you keep track? How do you manage that complexity, especially for retrieving old designs or planning manufacturing?
Good question. Engineers use classification systems, basically codes for parts. There are 2 main flavors you'll see. Monocode. Yeah, it's hierarchical. Think like a library system, Broad category, then subcategory, getting more specific, like animals, then mammals, then primates, then humans.
Got it. And the other type?
Is polycode, or sometimes called feature-based. This is more like using filters when you shop online. You tag a part based on specific features. Does it have holes? Is it round? What material? Regardless of its parent category.
Okay, more flexible in some ways?
Can be. The sources mentioned a really detailed example, an 8-digit code. It captures shape, key features, size, precision level, even the material. With 8 digits structured like that, you can represent something like over 25 million unique part families.
25 million. That's incredible granularity. It's like a universal language for parts within a company.
That's the goal. It helps you find if you've designed something similar before or helps automate the planning for how to make it. Saves reinventing the wheel.
Okay, so strategy set, parts are organized. But before we physically make anything, we need to predict how it's going to behave. That means math, right? Mathematical models.
Absolutely essential, because the things we design, they're dynamic. They move. They change over time. A robot arm, suspension, airflow over a wing.
They're not static.
Exactly. So mathematical models, usually differential equations or difference equations, are how we write down the rules.
Yeah.
They say, based on where the system is now, here's where it's going to be next. It's prediction, quantified.
And there's a kind of unified theory for this. Control engineers don't need totally different math for electrical versus mechanical systems.
It's one of the beautiful things, actually. We use these idealized system elements, think of them as building blocks. Some store energies like a spring or a capacitor. Some dissipate energy like a damper or a resistor. Some transform it.
And these same blocks apply across different physical domains.
Broadly, yes. You can model mechanical, electrical, fluid, even thermal systems using these core energy concepts. It gives us a common language.
And the modern way to express this, especially in control theory, is the state variable model.
Yeah, that's become really central. It's a very compact way to package up the system's dynamics. You use vectors, a state vector, usually 6x2, that captures the system's internal condition.
Like position and velocity?
Could be, yeah. Then an input vector, representing external forces or signals acting on it. And an output vector, for the things you can measure or care about. It's powerful for handling complex, multi-input, multi-output systems.
And this model lets you analyze the system's response, how it reacts to inputs.
Precisely. We look at things like transient performance. When you kick the system, does it overshoot the target? How quickly does it settle down to a steady state? These are critical for performance and safety.
How do you measure that?
We often analyze it in the frequency domain using poles and zeros. Their location on the complex plane tells you a lot. And for simpler systems, like standard second-order systems, think mass spring damper, you can calculate things like overshoot and settling time exactly.
Based on what?
Based on two key parameters. The damping ratio, which tells you how much oscillation there is, and the natural frequency, which tells you how fast it wants to oscillate. Knowing the poles and zeros, which come from these, instantly tells an engineer if the system is stable, if it's sluggish, if it's too bouncy. It's the mathematical core of stability analysis.
Okay, so math predicts behavior. Now, let's get back to the physical world, making sure the actual parts meet the specs. You mentioned materials earlier. They're complicated.
Oh, incredibly. Even defining a property isn't always straightforward.
Yeah.
Take hardness. Seems simple, right? How resistant is it to scratching or indentation? Well, the sources point out there are at least 15 different common tests for penetration hardness. And guess what?
They give different numbers.
They all give different numerical results. So just saying a material has a certain hardness isn't enough. You have to specify which test was used. It highlights how critical standards and clear communication are.
15. Wow. Okay, so assuming we can specify the material, what about efficient manufacturing? Powder metallurgy, PM, sounds interesting.
It is. It's a neat process. You take very fine metal powders, press them into a die shape, and then heat them, sinter them so the particles bond together.
And the advantage?
Several big ones. First, usually very little material waste, unlike machining where you cut away material. Often the part comes out needing no extra machining. It's net shape or close to it.
Saves steps and material.
Exactly. Plus, you can get unique properties. You can control the porosity, leave tiny gaps, which is great for filters or for making self-lubricating bearings. The pores hold oil.
Clever. What about processes involving deformation, like hot working?
Right, so hot working means shaping the metal plastically, permanently deforming it, but above its recrystallization temperature. Now, hot is relative.
How so?
Well, for lead, that temperature is basically room temperature. But for some steels, you're talking 2,000 degrees Fahrenheit or even higher.
Okay, let's talk about extrusion. Pushing metal through a shaped hole, a die.
That's the idea. Works great for aluminum, copper, but steel. Steel's tough. Its yield strength is very high, even when hot. Under the immense pressure of extrusion, it really wants to friction weld itself to the steel die.
Which would be bad.
Catastrophic, yeah. So for extruding steel, you need serious lubrication technology, often phosphate coatings on the steel billet, or even using molten glass as a lubricant layer between the hot steel and the die.
Molten glass as lubricant, that's wild. And piercing. Making seamless tubes, how does that work without a seam?
It's counterintuitive. You heat up a solid cylindrical billet, then force it over a pointed mandrel while it's also rotating. The forces cause the metal to shear in a specific way, and it actually creates a crack, an opening, right in the center of the billet, ahead of the mandrel. The mandrel then just enlarges and smooths out that internally generated hole into a tube. It relies on controlled failure, in a way.
Fascinating. A controlled internal crack.
Okay.
Parts are made. How do we ensure consistent quality? Statistical quality control, SQC?
Right. You can't inspect every single dimension on every single part, usually. It's too slow and expensive. So you use statistics. Control charts, like X-bar and R charts, are common tools.
What do they track?
The X-bar chart tracks the average of samples over time, showing if the process center is drifting. The R chart tracks the range within samples, showing if the variability is changing.
And there are rules for interpreting these charts.
Yes. One key rule of thumb mentioned is, if you get, say, 5 to 7 consecutive points all falling on the same side of the center line, even if they're still within the upper and lower control limits.
Something's likely shifted.
Exactly. It suggests a non-random change has occurred in the process, and you should investigate, even if you aren't making bad parts yet. It's an early warning system.
What about the process's inherent capability limits?
That's crucial. Capability limits, often calculated as the process average plus or minus 3 standard deviations, tell you the natural spread of the process, where 99.73% of the output is expected to fall if the process is stable. Now, here's the critical comparison. You compare those capability limits to the tolerance specified by the design engineer, the required precision.
And if the tolerance is tighter, narrower than what the process is capable of,
then you have a problem. That process physically cannot reliably produce parts within the required specification. You're guaranteed to make scrap or parts needing rework. Your only option then is 100% inspection, sorting good from bad, which is super inefficient. SQC helps ensure your process is actually capable of meeting the requirements in the first place.
Makes sense. Okay, let's shift gears from making things to powering them. Fluids and energy. First principles. What is a fluid?
Fundamentally, it's a substance that continuously deforms or flows when you apply a shear stress. Doesn't matter how small the stress is.
Unlike a solid.
Right, a solid will deform a bit under shear, then resist. A fluid just keeps moving. Think water, air, oil versus steel or wood. We also sometimes talk about ideal fluids, non-viscous, imaginary versus real fluids, which have viscosity, internal friction.
Got it. And the most famous equation here is probably Bernoulli's.
Has to be. It's basically a statement of energy conservation applied along a streamline in a fluid flow. It says the sum of the kinetic energy, due to velocity, the displacement energy, related to pressure, and the potential energy, due to height or elevation, stays constant. Foundational stuff.
When we need to move fluids, we use pumps or fans, turbomachinery. How are they selected? I heard something about fan pressure.
Yeah, the units. It's a bit quirky. Even though a fan moves gas, usually air, the pressure increase that creates the fan head is very often measured and specified in inches of water column, or in H2O.
Inches of water? For air?
Yeah, it's just an old convention that's stuck. It relates to the height difference in a simple U-tube manometer filled with water. For selecting pumps, though, a really important parameter is the non-dimensional specific speed, 2Ns.
Specific speed? What does it tell you?
It's a calculated value based on the desired flow rate, the required head pressure increase, and the pump's rotational speed. What it does is characterize the type of pump impeller geometry, radial, mixed flow, axial, that will be most efficient for that specific combination of flow and head. It helps you pick the right kind of pump for the job, ensuring it operates near its best efficiency point.
So it matches the pump design to the system's needs. Let's talk power generation gas turbines. They seem incredibly complex, especially with emissions controls.
They are. Modern gas turbines, especially large ones for power generation, have extremely sophisticated combustion systems to meet strict environmental limits, particularly for nitrox oxides of nitrogen.
How do they do that?
One key technology is the dry low-NOx combustor, or DLN. The dry means they don't inject water or steam, which used to be a common way to lower combustion temperatures, and thus not SOx. DLN systems use clever fuel nozzle designs and premixing chambers.
Premixing?
Yeah, they mix the fuel and air very thoroughly before they burn. The goal is to maintain a very consistent, lean excess air, fuel-air ratio everywhere in the combustion zone. This avoids localized hotspots where most NOx forms, allowing low emissions over a wide range of operating loads. It's tricky control.
And when we talk about efficiency overall, there's a concept beyond simple percentages. Exergy and EGM.
Right. Exergy, or availability, is arguably the true measure of energy quality or work potential. Standard efficiency often just compares energy in versus energy out. But exergy accounts for the irreversibilities in any real process friction, heat transfer across a temperature difference, things that destroy the potential to do useful work.
So minimizing lost work potential.
Exactly. And that leads to EGM, entropy generation minimization. Entropy generation is directly linked to exergy destruction. So EGM is a powerful, modern optimization technique. It tells engineers how to choose design parameters like the diameter of a pipe, the length of heat exchanger tubes, specifically to minimize the destruction of power, exergy, while the device does its job. It's a more fundamental approach to optimization than just maximizing simple efficiency.
That sounds powerful, but applying it must run into real-world messiness, like in heat exchangers.
Oh, definitely. Heat exchangers look simple on a diagram fluid.
Yeah.
A flows past fluid B, heat transfers. But in reality, getting the fluid to flow uniformly across all the heat transfer surfaces is a huge challenge.
What goes wrong?
The big issue is flow maldistribution. Some of the fluid finds shortcuts, bypassing the main heat transfer area. Some might leak between passes. The sources mentioned that in some situations, especially with viscous fluids and laminar flow, these ineffective streams bypass and leakage can actually account for as much as 60% of the total flow.
60%? That's crippling the performance.
It is. So, real heat exchanger design involves lots of clever mechanical details, things like adding bypass sealing strips inside the shell, just to force the fluid to go where it's supposed to. It's not just about the thermodynamics. The fluid mechanics inside are critical and complex.
Thinking bigger picture, system choices have global impacts. Refrigeration, for example. We hear about ODP and HGWP.
Right. Two key environmental metrics for refrigerants. ODP is ozone depletion potential. It measures how much a substance damages the stratospheric ozone layer relative to a baseline refrigerant, R11.
Okay, ozone layer impact. And HGWP.
That's halocarbon global warming potential. It measures how much a refrigerant contributes to global warming, again, relative to R11 over a certain time horizon.
So we moved away from ozone-depleting CFCs to HFCs.
Correct. HFCs, hydrofluorocarbons, generally have zero ODP because they don't contain chlorine. That was a success for the ozone layer. But many HFCs turned out to have very high HGWP values. They're potent greenhouse gases.
So solving one problem created another.
To some extent, yes. Now, the push is towards refrigerants, with both zero ODT and very low, or zero HTWP. Things like hydrocarbons, propane, isobutane. The challenge there is that many of these are flammable, which introduces safety considerations that the old inert refrigerants didn't have. It's complex trade-offs.
These efficiency and environmental concerns tie directly into managing energy use in buildings and industry, right? Energy audits.
Absolutely. An energy audit is basically a systematic investigation of how energy is being used and where it's being wasted.
What does an auditor look for?
It's usually two main things. First, eliminating unnecessary energy use altogether. Are lights or HVAC systems running when nobody's there? Can we use time clocks or occupancy sensors? Are there drafts, core insulation, what they call leak plugging? Simple stuff often yields big savings.
And the second thing?
Minimizing the energy required for the tasks that are necessary. Can we use more efficient motors? Can we optimize process heating? Can we recover waste heat?
Like with industrial furnaces. You mentioned they're more sophisticated now.
Yeah, exactly. Modern continuous furnaces, say for heat treating metals, aren't just big hot boxes anymore. They often have carefully designed temperature zones. Maybe a preheat zone using waste heat from hotter zones than the main firing zone, then a soaks zone to ensure uniform temperature.
Why the zones?
This zoned approach, this temperature profile, allows them to process more material, faster improve capacity, but do it without just burning way more fuel. It increases throughput and maintains fuel efficiency. Smart design.
So looking back, we've traced this path from grappling with human biases in the initial strategy.
Yeah, that messy human element.
To the rigor of mathematical modeling for predicting system stability.
Quantifying reality.
Then driving down costs and complexity with DFM&A.
The practicalities of making things efficiently.
And finally, chasing ultimate thermodynamic efficiency with concepts like exergy and EGM and power and fluid systems.
It really covers a huge range, doesn't it? From psychology to advanced thermodynamics.
It does. So what's the big takeaway for someone trying to grasp mechanical engineering? What's the core tension here?
I think if you boil it down, it's this constant balancing act. On one hand, you have the inherent variability and, let's face it, the flaws in human judgment, those cognitive biases we started with. You have to manage that.
Right.
But on the other hand, you're striving for absolute mathematical precision and physical optimization. EGM, state variable control, tight tolerances. You need designs that are rigorously engineered, cost-effective, safe, durable, and now increasingly environmentally sound.
Managing the subjective while pursuing the objective.
That's a good way to put it. Navigating that tension using structured processes and deep technical knowledge to bridge that gap. That, I think, is the real heart of the engineering mission we've been talking about. Keep your nuts torqued and spring-hard design junkies.